CSI. We can see that the ideal waveform of load voltage and load current. And then we have seen the capacitor commutated current source inverter. Yeah. So I hope all of you understand this operation of both the CSI, capacitor commutated and ideal current source inverter. Then we see the auto sequential current source inverter, in which we use the two commutating capacitor to turn off the thyristor. Now next is single phase series inverter. So single phase series inverter, you can see that circuit diagram. We have two thyristor T1 and T2 here, and in series with this T1 we connect the R load, and in series we connect the L and C, that is a commutating component. So this commutating component function is to turn off the thyristors. Okay. So here commutating components are connected in series with the thyristors, the series of circuit. So that's why it is called as a series inverter. So let's understand the operation of series inverter. As you saw that there are two thyristors T1 and T2 here. So first of all, by applying the Ig1 gate pulse to the thyristor T1, we first turn on the thyristor T1. At that time T2 is in off condition. So at that time only series circuit is formed by conduction of T1 in series RLC component. Keep in mind here R is only load, LLC component, that is your commutating component, which is used to turn off the thyristors. And assume that initially your capacitor is not charged. Yeah. So when you turn on this T1 at T is equal to 0, here you can see in the waveform. At that time what will happen, the current is flowing into the load, and same time the capacitor will be charged in the positive way, upper plate positive and lower plate negative. Clear? One thing is keep in mind here that you select the value of L and C in such a way that your circuit is become underdamped circuit. Underdamped circuit means that the current load current is become 0 earlier after current is reaching to the peak value. So you can see that here at this angle your current is reached to the peak value and after that become 0. Yeah. So once this current is become 0, what will happen? Your thyristor T1 becomes off because current flowing into the thyristor becomes 0 below the holding current. So thyristor is turned off. At that time your capacitor is fully charged because of the source current. Now after that what will happen? You can see that after point A to B, current flowing through the load is 0 because at that time no one thyristor is conducting, neither T1 nor T2 is conducting. Clear? So here you provide the sufficient time between A and B interval to the thyristor T1 to completely regain its forward blocking capacity. As you know that the thyristor, each thyristor requires some turn off time. Clear? So you can see that after point A, when current becomes 0, there is a sufficient time between A and B is turned, so that your thyristor T1 gets forward blocking capacity. And this turn off time must be more than the turn off time of the thyristor. Then and then your thyristor will completely off or regain its forward blocking capacity. Okay. So you can see that turn on time is this one and turn off time is between A and B terminal, which is more than the turn off time of the thyristor. So that your thyristor will completely commutated. Okay. At instant B, you can see that Ig2 is applied, this gate pulse to the thyristor T2. So thyristor T2 will turn on. But as you can see that at the same time the thyristor T1 becomes turned off by this commutating capacitor, because when 0 to A terminal, when a thyristor T1 is conducting, your capacitor is charged, current is flowing clockwise direction, upper plate positive, lower plate negative. You can see in this figure polarity. When T2 is conducting, when T2 is fired at instant B, this capacitor voltage is reversely apply across the thyristor T1. You can see the positive terminal is connected with the cathode and negative terminal is connected with the anode. So your thyristor T1 is reverse bias by applying the reverse voltage of this capacitor. So your by this capacitor your thyristor will turn off. Clear? Now at instant B, when you fire the T2, what will happen? Here current cannot be flow from the source because the thyristor is open circuited. But now capacitor is fully charged, so now capacitor is act as a source, and that capacitor is discharged through this T2 and loop. Now this is the circuit diagram. Capacitor, inductor, T2 and loop. Now in this direction, current will flow when T2 is conducting. So during the conduction of T1, your capacitor is charged, and during the conduction of T2, capacitor is discharged. So during the conduction of T2, you can see the direction of load current, that is exactly opposite as compared to the direction of current when T1 is conducting. Clear? Direction of current during conduction of T1 is this one, upside to low side, but when T2 is conducting, that is from lower side to upper side, right, in this direction. Clear? So you can see that the current flowing into the load is negative from B to C when T2 is conducting. Again, at instance C, when current flowing into the load is 0, where it is 0, where your capacitor is completely discharged. So current flowing into the load is 0. So at this instant, what will happen? The T2 thyristor will turn off. As you know, the holding current becomes, current flowing from the thyristor is below holding current, so it will turn. So at instance C, your thyristor T2 will off, and then after, you can see that capacitor again has sufficient, thyristor has sufficient time to completely turn off or regain its capacity. Clear? So by this way, your series inverter converts the DC into AC, and then provide the sufficient time to the thyristor to regain its complete forward blocking capacity. And here the commutating components are connected in series, so that's why it is called as a series inverter. All of you understand this concept of series inverter? All of you? Yes or no? Is there any doubt? Concept of series inverter?
सर
Yes.
सर ये बीच में ए से बी के बीच में ये गैप है, ये वाला दोबारा एक्सप्लेन कीजिए ना क्यों है?
Okay. So as you all know that each and every semiconductor device requires turn off time. Clear? When a current flowing from the thyristor becomes 0, it doesn't mean that at the same time your thyristor is completely off. Completely off means that it's completely not regain its forward blocking capacity. Clear? So each and every semiconductor device requires some turn off time. As you all know that, and you already learned from the PED one that turn on characteristic and turn off characteristic of thyristor. Okay. So as you know that some minimum time is required to turn off the thyristor. Okay. So at instant A, what will happen? The current flowing into the load is 0. It means what? Current flowing from the thyristor is 0. But at that instant, your thyristor is not completely off. It not completely regain its forward blocking capacity. So that requires some minimum time to completely off. So for that, we provide the sufficient time between A and B terminal to the thyristor to regain its forward blocking capacity. So that time is called as the turn off time, and that turn off time must be more than the turn off time required for the thyristor to regain its forward blocking capacity. Okay. Suppose you have the thyristor with the turn off time rating is 2 millisecond. It means that after current reaching to the 0 value, it takes 2 milliseconds to completely turn off. Clear? And this turn off time is, suppose it is 3 milliseconds. Between A and B, this instant is, suppose it is a 3 millisecond. So it means that your thyristor will completely regain its forward blocking capacity because it has sufficient time, 3 milliseconds, to completely off. Its rating is 2 milliseconds turn off time, and you provide the 3 millisecond time to regain its forward blocking capacity. But suppose this instant between A and B is 1 millisecond and thyristor turn off time is 2 milliseconds. What will happen? Your thyristor will not completely turn off. And if thyristor T1 is not completely turn off here, and at the same time at the instant B, if you turn on the T2, what will happen? Both the T1 and T2 is on. So your load will be bypassed and your source will be short circuited. Understand or not? So that's why you provide a sufficient turn off time to each and every thyristor to regain its forward blocking capacity. to avoid the short circuit of the supply. Clear now?
Yes, sir.
Okay. So let's move for the next topic.
સર
Yes.
સર ફરી વાર સ્લાઇડ કરો.
કયો ટોપિક છે ફરીવાર?
ના સર, ઓકે સર, આમાં કેપેસિટર નો જે ચાર્જિંગ કરંટ હોય યા એ અને બી પોઈન્ટ ની વચ્ચે ક્યાં ક્યાં પીક એનું પીક ક્યાં લેવા?
સોરી,
કેપેસિટર નો જે ચાર્જિંગ કરંટ હશે બરોબર,
હા,
એને એ અને બી ની પોઈન્ટ ની વચ્ચેનું પીક આવશે ક્યાં?
એ અને
આ એ અને બી પોઈન્ટ, એ પોઈન્ટ ઉપર લેવાનું કે બી પોઈન્ટ પર?
કેપેસિટર
ચાર્જિંગ કરંટ નો
કરંટ.
આપણે ગ્રાફ દોરીએ બરોબર, પેલા ચાર્જ થાય પછી ડિસ્ચાર્જ થાય.
See, when T1 is on, what will happen? Your capacitor will be charged. Okay. When capacitor is fully charged, what will happen?
ઇટ વિલ ડિસ્ચાર્જ નાઉ.
It will act as an open circuit.
એટલે એ થી બી પોઈન્ટ સુધી ઓપન રાખવાનું.
First of all, give the answer. Once your capacitor is fully charged, it is act as an open circuit. Yes or no?
સર પછી તો એ ડિસ્ચાર્જ થાય ને.
પહેલા ભાઈ ક્વેશ્ચન તો સાંભળો શું પૂછું છું. First of all, give me the answer. When your capacitor is fully charged, it acts as an open circuit. Yes or no?
યસ સર, યસ સર.
It means your circuit becomes open, current becomes zero. Okay. So at point A, your load current is zero. It means what? At that time, your capacitor is fully charged.
Fully charged.
Okay. When it is discharged, when you provide the closed path, at instant A, what will happen? Current flowing from the thyristor T1 is zero. At that instant, T2 is already off because you not applied any gate pulse. Okay. At instant B, just before instant B, you have both the thyristor in off condition. So this capacitor has not a closed path to discharge. But when you turn on the thyristor T2 at instant B, what will happen? Your capacitor will start discharging. Clear? And the direction of load current is what? Exactly reverse as compared to when thyristor 1 is conducting. Yes, that's why this load current is negative. Understand? So when T2 is conducting, what will happen? It is discharging. Yes or no?
Yes, yes.
And at instant C, what will happen? When it is completely discharged, the current flowing into this circuit becomes zero. So your thyristor T2 is off. But it takes some time. So between C to D, your thyristor T2 gets sufficient time to regain its forward blocking capacity. And at instant D, again you fire the thyristor T1. You can see that you apply the IG1. So again your T1 is on, T2 is off. Again your capacitor will be charged in the same direction. And current is flowing. You can see that. And again at instant E, your capacitor is fully charged. So at this time current becomes zero. Again sequence is repeated. Understand now?
Yes, sir.
Okay. Is there any doubt to anyone? Series inverter? Yes.
સર આ ઓમેગા આર કઈ ફ્રીક્વન્સી ને કઈ રીતે ફાઇન્ડ કરવાની?
Sorry?
સર આ જે ઓન ટાઈમ માટેનો જે ટાઈમ છે ને પાઈ બાય ઓમેગા આર, તો એ ઓમેગા આર કઈ ફ્રીક્વન્સી છે એમ?
That is the angular frequency, 2 pi f.
સર એ કઈ રીતે ફાઇન્ડ કરવાની સર એમ?
That is the radian per second. Radian માં calculate કરવાની. That is the time. See, pi divided by omega r. That is what? That is the time. Here. That is the time. You convert it this frequency or this angle into time. Omega is what? 2 pi f. Follow me. Omega is what? 2 pi f.
યસ સર.
That is pi divided by 2 pi f. It means what? It means what? It is 1 upon 2f. It is 1 upon 2f times this one.
Yes,
Can
sir.
I again? Hello.
Yes, sir. Means it's the equivalent representation of T by 2.
No, it is not T by 2, it is pi divided by omega. See, this frequency is depend upon the value of L and C. Clear? This frequency is depend upon the L and C. That is called as the ringing frequency. At which frequency this is under resonance condition. Okay. As I already explained that you choose the value of L and C in such a way that circuit is underdamped. Underdamped circuit માં શું થાય? આપણે આગળ જોયું સિંગલ ફેઝ ઇન્વર્ટરમાં. Before reaching to the half time, it becomes 0. So your half time is, see that, between 0 to t, but it becomes 0 before the half time at point A. Clear? So at how much ringing frequency your circuit is underdamped. So that time is this time pi divided by omega r. That is depend upon the value of L and C. कितनी value ली थी L and C में? Clear? It depend upon the value of this commutative component L and C. Yes or no? Under damp के over damp कोना ऊपर depend करे? That depend upon value of L and C. Clear? If your omega L is greater than omega C, then it is over damp. If it is less than omega C, then it is under damp. Clear? When your capacitive reactance is more than inductive reactance, in that case your circuit is work as an under damp, like this way, this circuit. In this circuit your value of Xc, that is more than XL. Yeah, that's why your current becomes 0 before the half time at point A. So this time from 0 to A point, or this pi divided by omega r, this time that depend upon the value of L and C. कितनी value ली थी? If your Xc is more than L, very high than XL, then this time is very less. Clear? If your value of Xc is near to the XL but higher than XL, then this time is near to the half time but less than the half time. Clear? So this time is depend upon the value of L and C. Under damped and over damped condition, in short, is depend upon the value of L and C. Clear? So this time pi divided by omega r, that depend upon which value of C and L you taken here. Clear? I think you clear the doubt this. Is there any problem? Series inverter? Anyone?
Sir, what is the role of inductor?
Role of inductor is what? Here to limit the source current. Role of inductor here is to limit the source current as well as to filter out the harmonics. Clear? Basically L and C, that is what? One type of passive filter. Clear? So whenever you switch on and off here T1 and T2, what will happen? You can see that your output is not a pure sine wave. Clear? So to remove the harmonics from this output current and limit the source current, you require the inductor. Clear? As you know the property of inductor that opposes the rate of change of current. Clear? So suppose that short circuit happen here in the supply side. Suppose resonance happen. Resonance condition, what will happen? X is equal to XL. So in that case your circuit, this part impedance becomes low. So very high amount of current is flowing from the supply. When T1 is conducting, suppose resonance is happen, so that will can damage your thyristor. Clear? So in that condition, to avoid the damage of the thyristor, you can put the inductors. Very high value of inductors. Clear? So there are two functions of inductor. One is act as a filter, and another is to limit the source current. Yes, sir. Any doubt here? Please turn off your mind. Please. Don't create the noise in the lecture. Is there any doubt to anyone? So can I move for the next topic?
Sir, what is the special application of the single phase series inverter?
Yes, very good question. The series inverter that is generally used for the induction heating and fluorescent lighting. Generally that is used for these two applications, induction heating and fluorescent lighting. And this inverter is generally operated at very high frequency, like 200 hertz to 100 kilohertz. Clear? That's why I'm saying that it is operated at very high frequency, so switch on and off time of this T1 and T2 is continuously. So that creates the large amount of harmonics into the output current. Yes, that's why you need the filter circuit and the load side also. Okay? And that's why generally it is used for the induction heating, because ultimately loss of power in the load that creates the heat. Yeah. So for an application where you require the generation of heat like induction heating, in that case you can use the series inverter. Okay?
Yes, sir.
Okay, so let's move for the next topic, parallel inverter. So let's see the circuit diagram here. Here again we use the capacitor for the commutation of thyristor. So first we see the circuit diagram. This is your supply, voltage source. In series we connect the inductor. So here the function of inductor is what? To make this source as a current source. Clear? Because this is the current source inverter, parallel inverter. So the voltage source in series with the inductor, that makes the current source. In series here you can see that we connect the two thyristor in parallel, T1 and T2. Here we connect the capacitor in parallel with the primary of this transformer. Here primary has two winding, primary upper half and primary lower half, and this is the secondary winding. Here we assume that each half of the primary and secondary has 1:1 turns ratio. Okay. So N1 turns in the upper half, same number of turns in the lower half in the primary, and same number of turns at the secondary side. N1 is equal to N2. Okay. So it is a 1:1 transformation ratio. So suppose that V1 voltage in the upper half of the primary, so same voltage V1 you can transfer at the secondary side. Clear? So that we assume here for this understanding the operation of this parallel inverter. So first of all you turn on T1, then after T2. Okay. Now why it is called as a parallel inverter? Because here we connect the commutating component in parallel with your load. You can see that secondary side the load is connected. Whatever the voltage at the primary side, that transfer to the secondary side. You can see the capacitive component C that is connected at the parallel with the primary one. So whatever the capacitor voltage that is reflected to the secondary side. So that's why it is called as a parallel inverter. Okay. Now let's understand operation. First mode, that is for t less than 0 time. It means before t is equal to 0 time, here we assume that your thyristor T1 is in on condition. So this is the equivalent circuit for mode 1 at t less than 0. It means before t is equal to 0. Or you can say that t is equal to 0 minus time. Now you can see that at this time the T1 is on, current is flowing from the supply to the transformer primary upper half and then negative terminal. Clear? At this time already your capacitor is charged with this polarity, plus or minus. Clear? Now what will happen with the primary, current is flowing from the primary through this T1, the voltage across the primary V1, that is what? Same as the supply voltage. Supply voltage is what? Here voltage across the capacitor is 2 Vs. So same 2 Vs voltage come across the whole primary winding. Primary winding, each primary winding has two parts. One is N1 turns and another is the N2 turns. So half of the primary has voltage how much? Vs. Okay. So this mode the voltage Vs come across the primary and that transfer to the load side. Okay. So let's see the waveform for this mode when T1 is in on condition. So let's see that this is a t is equal to 0 instant. Here the mode is before t is equal to 0. It means t less than 0. So at this instant you can see that voltage across the capacitor that is already charged with the 2 Vs. So it is constant 2 Vs. This is the capacitor voltage. Second waveform is voltage across the thyristor T1. So as you know that when thyristor T1 is conducting, there is no voltage. It means 0 voltage. You can see that. So 0 voltage across T1 from 0 to between this instant to t is equal to 0 instant. This is a t is equal to 0 instant. Now load voltage V0, you can see that is a constant voltage and is equal to Vs. Why? Because you can see that voltage across the whole primary winding is what? 2 Vs. Voltage of capacitor. Clear? But half of the primary winding, that is half of this capacitor voltage, because both have same number of turns. So your load voltage is Vs because upper half of the primary winding has Vs voltage. Yeah, because current is only flowing into the upper half when T1 is conducting. You can see this. This is the circuit diagram when T1 is conducting. So this is the output voltage, V0 is Vs when T1 is conducting, and capacitor current is 0 because your capacitor is fully charged to 2 Vs. So it is act as an open circuit. So there is no current is flowing into this capacitor. So capacitor current is 0. You can see here. At that time, you can see the thyristor T1 current that is flowing because it is on condition. So that is constant also because voltage is also constant Vs. So Vs divided by load resistance R, that gives the constant current I0 flowing from the T1. At this instant T2 is 0, T2 is not conducting, so current flowing to the T2 is 0. You can see. So this is the first mode for that different value of Vc, capacitor voltage, thyristor voltage, output voltage, capacitor current, thyristor T1 and T2 current. Clear? This is for mode 1 before T is equal to 0. Now at T is equal to 0 instant, you can see that you fire the T2. Yes?
ये कैपेसिटर के अक्रॉस में 2 Vs कैसे हुआ?
See here we assume that it is a steady state condition. So before T1 is on, your T2 is in on condition. So when T2 is on, that will charge the capacitor. Clear? We already put the capacitor which is already charged. Clear? We already put the capacitor which is initially charged at t less than 0 time. कैपेसिटर है ऑलरेडी चार्ज हुआ है, वो हम प्लेस कर रहे हैं अक्रॉस द प्राइमरी वाइंडिंग. क्लियर?
बट सर ये मैक्सिमम Vs पे चार्ज नहीं होगा, मतलब ये डबल कैसे हुआ Vs पे?
See, suppose you have the circuit diagram with the voltage of Vs. Suppose Vs is 100 watt. So you take the capacitor of 200 watt with the charging 200 watt full capacitor. Clear? So that is just for understanding that here whatever the supply voltage as double capacity of capacitor put here across the primary winding and charge it, and then connect across the primary winding. Clear? Suppose your Vs is 200, so take the capacitor of 400 watt with fully charged when T1 is on condition. Clear?
Okay, sir.
Here again I repeat that the function of this capacitor is what? To turn off the thyristor. That we will understand in the next mode why we use this capacitor is initially charged. Clear? As you say in the series inverter and capacitor commutated inverter, that in that also we have assumed that initially charged. Why? Because we want to turn off the thyristor by capacitor. Clear? So that's why it is called as a capacitor commutated current source inverter. Clear? So same here, the capacitor function is what? To just turn off the thyristors. Clear? Okay, let's see the second mode. T is equal to 0 plus instant. It means just after T is equal to 0, when you turn on the thyristor T2. So you can see that this is the thyristor T2. You close it. At this time, initially as you know the capacitor is fully charged with 2 Vs. Now what will happen? When T2 is fired, now current is flowing from the supply and flowing into the thyristor T2, lower half of the primary winding, and then negative. Why your T1 is off here? That is off because of this capacitor. As you see that capacitor is fully charged with 2 Vs, upper plate positive, lower plate negative. Clear? Now when you fire the T2, what will happen? Your positive of this capacitor that is connected with the cathode of T1 and this negative terminal through this T2 that is connected with the anode. So what will happen? Minus 2 Vs reverse voltage come across this thyristor T1. So as you know that when you apply the large reverse voltage across the thyristor, it will turn off. Clear? So here you can see the function of the capacitor is what? To turn off the outgoing thyristor. It means T1 here. Same way in the next mode, this capacitor will turn off this thyristor T2 also. Clear? So that's why we assume that it is initially charged, so that can able to turn off the thyristor. Now I think all of you understand that why we initially charge the capacitor. Clear? All of you understand how this T1 is turned off? At instant t is equal to 0. અહીંયા સુધી કોઈ doubt છે? Yes? Anyone?
सर एक बार रिपीट कीजिए ना.
Okay. As you know the different commutation technique of thyristor. When your thyristor is turned off, give me the answer. When your thyristor is turned off,
When it will get reverse current.
yes, when it get reverse current or reverse voltage, yes or no? When you apply the high reverse voltage, then also it can be turned off. Another way is the natural commutation, when your supply is naturally becomes 0. But that cannot possible here because your supply is DC, that is constant DC. So naturally your supply never becomes 0. So here natural commutation will never happen. Clear? So but here you provide the reverse voltage of this capacitor across the T1. So because of that your thyristor T1 is off here. And when it is off, when you turn on the T2 here, so you can see that at mode 2 at t is equal to 0 plus, when you turn on the T2, so for very short instant of time both the T1 and T2 is on. So this positive of this capacitor is connected with the cathode. This is the cathode of T1, and this negative through this T2 that is connected with the anode of T1. So there is a reverse voltage across the T1, and that is 2 times supply voltage. Clear? So because of this high reverse voltage across the T1, that will turn off your thyristor. Clear? It means it regains its forward blocking capacity, so it is act as an open circuit. And just after t is equal to 0 plus, only T2 is conducting, so current flowing from the supply inductor T2 lower half of the primary winding and then negative. Now understand all of you this thing?
Yes, sir.
Okay. So let's see the waveform for this condition. What will happen? At this time, when T1 is T2 is conducting, at this time the capacitor is also discharged through this transformer winding. You can see that the capacitor current is flowing into the clockwise direction, which is discharged into this primary winding. Clear? So first of all, it discharged from 2 Vs to 0, and then it is charged from 0 to minus 2 V. Let's see that the mode 2 in the waveform at t is equal to 0 instance, what will happen? So here you can see that t is equal to 0 instant, T2 is on. In that condition, you see the capacitor voltage Vc, that is decreasing. Why it is decreasing? Because it is discharging. You can see here, initially it is charged to 2 Vs, clear? But now it is discharging into the primary winding. So capacitor voltage is decreasing. You can see that in the waveform, capacitor voltage 2 Vs, that is decreasing. Once it is fully discharged, becomes 0. So at this instant, capacitor voltage becomes 0. And then after it is charged into the negative direction and reach to the maximum value minus 2 Vs. So one is reached to the maximum value, again it is active as open circuit. So that continuous remains fully charged minus 2 Vs. So in this duration it is active as open circuit. Now at this time you see the value of thyristor voltage T1. As I know that when you fire the T2 here, t is equal to 0 instant, the capacitor voltage, these 2 Vs reversely come across the T1. You can see that thyristor voltage. At this instant, the voltage across T1 is minus 2 Vs. Yeah. And then after you can see that this voltage across T1 is decreasing because your capacitor voltage is decreasing because it is discharging now. Clear? So in this time, when you provide the minus 2 Vs reversely across T1, your thyristor is regained its completely forward blocking capacity. So this time is sufficient. This TC time, which is the reverse voltage across T1, is sufficient to turn off the T1. As we see in the series inverter, we require some turn off time for the thyristor. So you provide some minimum time to completely regain its forward blocking capacity. So here also in parallel inverter will provide the sufficient time Tc to completely regain its power blocking capacity of the T1. Clear? Now at the same time we see the output voltage. Initially conduction of T1, your output voltage is Vs, but after that you can see that the output voltage is decreasing. Why? Because your capacitor is discharging now. So as the capacitor is discharging and capacitor is connected to the primary winding, so primary winding voltage is decreases. So same way secondary side voltage is also decreasing. You can see that here. As capacitor is discharged, capacitor voltage decreasing. So at the secondary side, the voltage induced that is also decreasing. So secondary voltage V0 is also decreasing. Clear? So that's why load voltage is decreasing. And once the capacitor becomes zero voltage, your load voltage also becomes zero. And when it is fully charged in negative direction, minus 2 Vs, the load voltage reaches to the minus Vs. Clear? Because here you get the load voltage from the only one half of the primary winding. Now during the conduction of T2, only secondary winding is in the picture because there is no current in the primary winding, load current. Clear? So only minus Vs current during the conduction of, minus Vs voltage during the conduction of T2. Now at the same time you see the capacitor current. As you see the capacitor is discharging, so capacitor is also discharging, so that current is also reducing. And once the voltage is zero, current is also becomes zero. And once it is fully charged, it is acted as open circuit. So you can see that in open circuit there is no current flowing into the capacitor. So current is zero. Clear? Why here negative sign is taken for IC capacitor current? Because we assume that the positive direction of capacitor is current from top side to bottom side. This direction. You can see here it is indicated in the figure. This is a positive direction. But when capacitor is discharging during the conduction of T2, you can see the direction of current is opposite to the indicated direction. So that's why we take the IC is negative. So this IC is negative during the on condition of T2. Now you can see that the T1 is 0, current of T1 is 0 because it is off condition, and current in the T2 is flowing because it is in on condition. Yeah. So it is remain on until the next T1 is fired. So T1 is fired at T by 2 instant. Here you can see that. So up to this instant your T2 is remaining on condition. Yeah. So now let's see the mode number 3, that is instant between T1 to T by 2. It means instant this one T1 to T by 2. Here T1 instant, what will happen? Your capacitor is fully charged but with the reverse polarity, minus 2 Vs. Minus 2 Vs means lower plate positive, upper plate negative. Clear? And T is equal to T by 2 instant, what will happen? You again fire the T1. So in between this instant, what will happen? You can see this. Your capacitor voltage as it is. Clear? Your voltage across the thyristor is positive 2 Vs because that is applied now. Positive polarity. You can see that positive is connected with this positive of the capacitor is connected with the anode of T1 and negative is connected with the cathode of T1. So 2 Vs, that is positive voltage, come across the T1. But it will not turn on because you not fire the T1. Clear? You fire the T1 at T by 2 instant. So that after that current is flowing into the T1. Clear? So this is the mode number 2 between T1 to T by 2 instant. So that current is flowing into this T2, lower half of the primary winding and then negative of the secondary. Clear? At that time your capacitor is fully charged to minus 2 Vs here. In mode number 3, just after T is equal to T by 2, it means this instant when you fire the T1, again you can see that Ig1 is applied here. Clear? So when you fire the T1, what will happen now? You can see in the mode of operation, when you fire the T1 at the instant of T is equal to T by 2, at the same instant for some instant of time your T2 is also in on condition. So this capacitor is fully charged with the minus 2 Vs, and when you turn on the T1, what will happen? This capacitor voltage reversely come across the T2. You can see the positive is connected with the cathode and negative through this T1 because it is on at T by 2. that is connect with the anode of T2. So this reverse voltage of capacitor come across the T2 and that will turn off your T2, so it acts as the open circuit. So now you can see that in mode number 3 your T2 will off by this capacitor. Clear? So now current is flowing from supply to T1, upper half of the primary winding and negative of the secondary. And at the same time your capacitor will discharge. You can see that now capacitor discharge and current flowing into anti-clockwise direction. You can see that. So first your capacitor is discharged from minus 2 Vs to 0 and then again it is charged to 0 to 2 Vs. Clear? So let's see the waveform so they can understand here. So at t is equal to t by 2 instant, when you fire the T1, you can see here at this instant, when T1 is on, your capacitor is discharged first minus 2 Vs to 0, and at that time voltage across the T1 is what? 0, because it is on condition. As you know that on condition there is 0 voltage across the T1. Now voltage across the load, you can see that that is increasing. That is increasing because now T1 is conducting, so voltage across the load, that is increasing. Now current flowing from the capacitor, you can see that that is decreasing from positive to 0 because your capacitor is discharging now. See the direction of current, that is a positive direction, this one. Okay, so that's why you take the current as a positive, but it is discharging, so it is decreasing. And once it is fully charged at 2 Vs, act as an open circuit, so capacitor current becomes 0 at this instant. Clear? So this is the current of capacitor, and this is the value of thyristor T1 current at t is equal to t by 2 instant. As you turn on the T1, so current flowing start from the T1 from this instant until you fire the T2 at next instant of time at t is equal to t. At the same time, current flowing in the T2 is 0 because it is off by this capacitor. Clear? So again, this thyristor is remain continuous conducting up to the instant t, and then after again you fire the T2. So this cycle is repeated continuously. Same like here. You can see here it is discharging. So here same way, when you fire the T2, again it is discharging and then turn off the T1 by the capacitor commutation. Clear? So this cycle is repeated for the next cycle also. So there are 3 modes. First mode, t less than 0, T1 is on, this is the equivalent circuit. Mode 2, t is equal to 0 plus, at this instant you fire the T2 and at that instant your capacitor is commutate your T1 by reversely applying the voltage. In mode number 2, again this is the mode number 2 between T1 to t by 2. So that instant your T2 is remain conducting, but at this time your capacitor is fully charged, so it is act as open circuit. Next mode number 3, at t is equal to t by 2 instant, when you fire the T1 again, your capacitor is reversely charged, so that will commutate your thyristor T2, and now again current is flowing into the upper half of the primary winding and capacitor will discharge to 0 and then again charge with the positive direction. So this is the operation of parallel inverter. You can see the waveform of output voltage, that is a sine wave, not exact sine wave, but it is a square type of the sine wave. Again, if you want to remove this harmonic, you can use the filter at the load side, secondary side of this transformer. All of you understand this operation? Yes or no?
Yes, sir.
Okay. I think it is little bit complicated to you to understand this, but if you read this again and again, if you see the circuit diagram, equivalent circuit diagram and then waveform, then I think it is very easy to understand. Clear? So I suggest you that whenever you read this theory of series of parallel inverter, see the waveform and equivalent circuit for different mode and try to understand it. Like here we see the first mode. So at this instant we know that T1 is on. So what will happen here, you can see in the circuit diagram as well as you can observe in the waveform. Clear? Without observing the waveform you cannot understand what will happen in the equivalent circuit. Clear? So first of all, try to understand the first mode. What will happen in the mode 1 when T1 is on. If you understand this, then after switch on to the mode number 2. It means at t is equal to 0 when t2 is 5. So see the circuit diagram, what will happen in mode number 2. So try to think about this, what can happen, and then after see the waveform for all this quantity like voltage across T1, T2, current flowing in the T1, T2, thyristor current, capacitor current and load voltage. So if you try to understand this mode by mode, then you can understand it. If you mug up this waveform, then I think it is not way to understand this parallel series inverter. Yeah. Not only this topic, but any topic of this power electronics, if you try to understand the concept of any circuit, you must understand the waveform of this circuit diagram. Yeah. If you clearly understand the fundamental of inductor, capacitor, then I think it is not that much of difficult for you to understand the operation of any converters. Yeah. So you must complete the fundamentals of your inductor and capacitor. All of you must know that what will happen when your capacitor is fully charged, what happens in the steady state condition in the capacitor, what happens in the inductor. All of you I think know that control circuit માં ભણી ગયા છો, initial condition and final condition. Clear? So what is initial condition? Initial condition means when you initially energize your inductor and capacitor. So what is the behavior of inductor and capacitor when you initially energize? Open circuit or short circuit? Same way in the steady state condition. Steady state condition is final condition. So once you provide continuously supply voltage and current to the inductor and capacitor, what is the behavior of it? It is acted as short circuit or open circuit. Clear? So this concept must you know that then and then you can understand the operation of any converters. This is basically for this theory, series and parallel inverter. So here I complete this topic as well as this chapter number 1, inverter. So in your first internal, that is in the next week, the whole chapter of this first inverter that you complete, the syllabus for first internal, chapter number 1. Clear? And I already provided the question bank, but that question bank is tentative. It doesn't mean that I ask the question only from that question bank. Clear? Some of the question may be out of the question bank also. Clear? So the question bank given to you, that is just for your reference. Don't take that as a like all the questions of the exam that ask from the same question bank. Clear? Okay. So next, let's start the next chapter number 2, AC voltage control. कोई डाउट है chapter number 1 is there any doubt to anyone? So I can move for the next topic. Yes, anyone?
No, sir, not now.
Okay. So it is my request to all of you that for the next internal, all of you start reading already. Sorry. Yes. Any question to you? Any question here? Okay. So all of you have time of 1 week. Not only 1 week, but I think 2 or 3 days. Because next week your internal exam will start. So if you have any doubt in chapter number 1, you mail me or you can call me. So all of you please start reading this chapter number 1 from P.S. Bimra, chapter number 8. Clear? Also you can read this chapter from Khan Chandani book. जो हमारे पास है तो available. Clear? But I think this book is sufficient to understand this all the topic of inverter P.S. Bimra. Clear? So let's move for the next chapter, AC voltage control. All of you able to see this? That one?
Yes, sir.
Okay. So, as we know that there are different types of converter that we already classified here. So, in that converter, AC voltage controller is the one of the converter. which is the AC to AC converter. AC to AC converter. As we know that there are two types of AC to AC converter. One is this AC voltage controller, and another is cyclo converter. So both this converter, AC voltage controller and cyclo converter, both are AC to AC converter. It means that converts AC to AC. Your supply is AC, your output is AC. But what is the difference between these two converters? In AC voltage converter, that converts your fixed AC voltage into variable AC voltage without changing the frequency. Without changing the frequency. Suppose this is the AC voltage controller. This is your 50 Hz 230 volt AC supply. At the output side, you may get 200 volt, but of the same frequency, 50 Hz. It means this AC voltage controller just change the magnitude of input voltage at the output side. Clear? Whereas the cyclo converter that control the output voltage as well as control the frequency. So in the cyclo converter, you apply suppose with the 50 Hz frequency 230 volt. So at the output, you may get output frequency more than supply frequency or less than supply frequency, whatever you require. That depends upon which type of cyclo converter you use. There are different types like step down cyclo converter and step up cyclo converter. So your output frequency is more or less than supply frequency, and that also controls the output voltage. So that is the difference between these two AC to AC voltage controller. AC voltage controller just control the magnitude of output voltage without changing the frequency, where cyclo converter control the magnitude of voltage as well as changing the output frequency. Clear? I think all of you understand this difference between AC voltage controller and cyclo converter. Both are AC to AC converter. So this chapter we will discuss in the next after completion of this AC voltage controller. So this chapter we understand the concept of AC voltage controller, where we convert fixed AC voltage to variable AC voltage without changing the frequency. Clear? So let's understand this operation by simple example or simple circuit diagram of single phase half wave AC voltage controller. So suppose this is your supply of 50 Hz 230 volt. This is your thyristor T1. Suppose this is the diagram. And here we take resistive loop. This is a simple half wave AC voltage controller. Why it is a half wave AC voltage controller? Because it controls the only half cycle of your supply. Let's see the waveform so that we can understand it. Suppose this is your supply voltage V, this one. This supply voltage is provided to this parallel combination of T1 and diode. So here, suppose that you fire your T1 at 0 instant here. So what will happen? The current starts flowing from the supply through T1 and loop because it is acting as a closed switch. When you fire, the T1 and instant 0. Clear? So what is the output voltage V0? Full half cycle of supply you get across the load. So you can see that full half cycle you get across the load. Same way here, your diode is conducting during the negative half cycle. Why? Because in positive half cycle, positive negative here, diode is reverse biased. So it is acting as an open circuit during first positive cycle. Clear? So only T1 is conducting. So positive supply voltage you get same as the supply, and During negative cycle of supply, it means this cycle, your diode D2 is conducting like this. Clear? So, full negative cycle of the supply, you get across the load side. It means whatever the supply voltage, same voltage you get the load side. But what is the difference here? Here you have using the thyristor. So by using the thyristor, you can control your half of the cycle here, positive half cycle. Here we fire the thyristor T1 at 0 speed, but suppose you fire the thyristor at alpha is equal to 30 degree. Suppose here we apply the gate pulse, thyristor T1. So what will happen? The output voltage across the loop that will start from alpha 30 degree here. So between 0 to 30 degree, your thyristor is in off condition. It means at the open circuit. So there is no transfer of power from supply to load. So 0 voltage. And fire the thyristor T1 at alpha 30, it is at the closed switch. Current is flowing into the loop. So whatever the angle 30 degree here, whatever the magnitude of supply voltage, same magnitude of output voltage you get at the load side. This one. So you can see that by using the thyristor, you can control the magnitude of output voltage. But in this circuit, you can control only half cycle. So that's why it is called as a half wave AC voltage control. Because in the negative cycle, your diode is conducting, so you cannot control the magnitude of negative cycle, because just after this instant, your diode will be forward bias, because you are not requiring gate pulse, because you have not any control over the diode once it is forward bias. So you get the full negative cycle across the load. So that's why it is called as a half wave AC voltage control. It controls only half cycle of your supply. But suppose if you use the two thyristor here, so it means that you can control positive as well as negative cycle of your supply. So that now the circuit diagram becomes full wave AC voltage control. Full wave, because it controls the positive as well as if this thyristor T2 is fired at the same angle here. So again you can control the negative cycle this way. So if you take the average of this output voltage, that is less than the supply voltage. Okay. So by this way, by changing the firing angle of T1 and T2, you can get the variable output voltage across the loop. But again, you can see the frequencies remain same. This is a 50 Hz frequency, so this is the output voltage of the 50 Hz frequency. So this is why it's called as the AC voltage control. So I hope all of you understand the basic concept of AC voltage control. In the next lecture, after the internal, we will go into detail about this full wave AC voltage controller and then other types of the AC voltage controller in detail. Okay? So here I stop this lecture because I think time is over. So all the best to all of you for the internal exam. As I told you that first internal, your syllabus is chapter number 1, inverter. The question bank which I have given, that is the only tentative question bank. It doesn't mean that I ask the question from same question bank. Question may be different in the exam. Clear? Some logical question may be asked. So please prepare accordingly. And please don't mug up the waveform of all the circuit diagram. Try to understand it. If you have any doubt, please ask me the question. Okay? So here I stop this lecture. If you have any doubt, please ask the question. Otherwise, you can leave this meeting.